One problem about working with computers is their unforgiving nature. One tiny slip can throw them and you into complete confusion. In other words, we're having to adapt the way we want to work to the limitations of the computer as it is today. One possible way out of this is to be able to communicate with them in a way that we're used to. For example, by talking to them, or even by writing them notes.
Tie. Sweater.
Recognizing the human voice has proved to be one of the greatest challenges for the computer scientist. In this demonstration, the operator speaks single words which the machine matches against pre-recorded patterns in its memory.
Trousers. Vest. Coat. Coat. Jacket.
This automatic speech
Sweater.
recognition system gets it
Tie.
right about 90% of the
Coat.
time.
Vest. Blouse. Presently, the technology, although it's been around about 20 years, is in a relatively early stage. It would be very nice to be able to walk up to an ASR device and be able to speak in complete sentences without having to train it. Most of the devices that are currently on the market require you to speak in isolated words with a certain pause in between each word, and require you to train the voice to your particular speech patterns. There's research going on all the time, and we're gradually moving towards our goal of continuous speech.
How long is it going to be before I can phone home and say, cook dinner, and it works?
It may be sooner than you think, but it will still be probably within the next decade, something like that.
At IBM's research labs near New York, important work, which we weren't allowed to film, is being carried out on voice recognition. Success in this field could be enormously significant for office automation. So too would a breakthrough in recognizing the written word, where the technical challenge is not so much the hardware, they've already got electronic paper and electronic ink. The challenge is understanding the problem and writing the software.
How does it work, Robin?
I'm writing these characters, as you can see here, on this gas panel display with this pen and the electronic ink. And what's happening is, as I write each character, it's being compared with samples of my own handwriting, which I put into the computer before. So at some time in the past, I've written a B, and I've told the machine that that's the way I write a B. Now, as I write these unknown characters, each one is compared, in turn, against all the samples that it got. So it's compared against the A, the B, the C, the D, right the way through the alphabet.
Both in upper and lower case?
In upper and lower case, and of course the numerics are also in there as well, and if you want to extend it to put punctuation in and so on, you put all of those in. So you actually compare every incoming character against all the samples of handwriting, and the one which matches best is chosen as the answer.
What's the ultimate goal of this?
The ultimate goal is to build a terminal which you can put on somebody's desk, which is, first of all, it's flat, rather than, you know, this great big display like this one, keyboard all sitting in front of you, coming between you and your client, for instance. It's got to be flat. It's got to be exceedingly easy to use. And keyboards are not that easy to use, especially for a large number of us. We still have to hunt our way around, find the keys we want to press them, then look up at the screen to see whether it all worked or not. We want something which works in a much more natural way than having to press keys on a keyboard and look at characters and move cursors around displays. Now here, what we're doing is everything happens on the one surface. The output is in printed text that you and I can read. The input is in your own handwriting. And hopefully, I don't have to teach people how to write their own handwriting. What I do have to do is I have to teach the computer system how to recognize it. So what we have to do is we have to take the system from where it is today, where we can do these characters that aren't joined up and characters that are all joined up, into doing what people really do, which is to write in a mixture, where some of the characters are joined up, some of them are overlapping, some of them are not overlapping. And we've got to make it work with much more natural styles of handwriting.
I receive information from the outside world in many forms. Letters, schedules and timetables, and different sorts of reports. And I need a way of getting them into the machine. Not simply as facsimile copies, but so the machine actually reads the information captured in these reports so that it can subsequently analyze it. At another of IBM's research labs in California, they're working on ways of getting existing text into the computer.
First of all, the work we're doing in this department in the area of the document systems is to provide support for both the creation of documents and also for the storage and retrieval, archival of existing documents. And those two sort of blend, because at times we want to take parts of old documents and use them to make new ones. So we'll be handling both the scanning of documents that could be as old as this Scientific American from 1845. When this was made, there wasn't any technical support for creation of documents like this. We'd like to put it into a system where we can work with it, retrieve information from it, find references to patents of George Westinghouse on the threshing machines, be able to do textual retrieval and information search.
For the document to be read, it's first scanned in a facsimile machine, which makes a copy of it, rather like taking a photograph.
Well, here is the result of scanning that page of Scientific American. So the computer now has that page in its memory, but it has it there essentially like a television picture. So that looks to you and me like the letter S or the letter C, but the computer just has an image, just a little picture of that. And what we want to do in order to be able to do document retrieval, of finding words, the computer has to have those words in the computer form. And so that's the process that we're involved in, developing the software that will translate pictures of scanned letters into letters that the computer can then process and do other work on, so that we can use them to edit, so that we can add them to a document, so that we can do retrieval and searching and other computerized tasks.
The text is isolated from what we would call the graphics. This is done by eye. The computer examines the image and produces a list of all the separate shapes it finds. Some aren't letters at all. It doesn't know what they are, so it has to be told by a human who identifies each one by entering its equivalent on the keyboard, making a guess at the broken letters. Since there aren't many, it doesn't take long to do this. The computer is now capable of looking at the whole text as if it had been typed in. So now it can be edited and searched in the normal way.
Of course, we've been involved in publishing documents, technical reports, and providing the kind of support that we need for that publishing. And those documents contain not only text, which we've done very well in the past with computer systems, but also images and graphics. And inclusion of those in a document and electronically doing the task that's now known as cut and paste is a major effort that we've developed with the system that we call Janus. And an example of that might be in a catalog of parts and a couple of pages that I've torn out, one a drawing showing the fuel system, and the other a set of photographs showing the procedures for adjusting that fuel system so that maintenance procedures can be carried out. Well, the result of scanning this page is that we now have in the computer this image of that page, and I want to crop out a section of that so that I can use it in a technical document. So I have essentially electronic scissors here, and I have that little diagram that I just created in the middle of this page. So I'll now grab that image, and I will move it, let's say, over here to the top of this column. And now you see the result of my electronic cut and paste, where I've now put both the photographs and that drawing on one page. So someone who's reading this text will see the figures at the same place where they're reading them.
This system knows the rules of layout for a technical document, and it applies them in an apparently intelligent way to produce a well-laid-out result very quickly. At a library in New York, you can see the way a similar problem has been solved for the blind by a device invented by Kurzweil, a small company in Boston.
Fall classes. Thank you also for the hospitality you shared with us during the training.
It can scan the printed word and read it out aloud, adapting to and learning most styles of print, and give a reasonable reading of well-formed text. When it can't cope, the operator can get the machine to spell things out letter by letter.
T-H-O-R-O-U-G-H.
Not surprisingly, the company has been bought up by one of the large office equipment suppliers who aim to use it for business applications. Meanwhile, another kind of expert system is being devised to mimic what we do when we turn to reference books to check spelling, grammar, and even style in a written document. Some aspects of written language are subject to precise rules. Spelling is an obvious example. An expert system combines a linguist's knowledge of the rules of grammar with the know-how of the computer scientist to produce useful software, in this case capable of checking text for inaccuracies.
What I have here is an example of a letter. It's a letter that we've constructed ourselves, so it has many more errors than we normally find in a piece of human-generated text on a computer. So we've got, on top of the letter, there's this tag which allows you to select lexical, grammar, or style errors, or there's a mode in which all errors are shown to you at the same time. And then in the body of the letter, you'll see several words are highlighted in red, showing where the system has found potential errors, which it wants to bring to your attention. And what you can do then is to select one of the errors using the light pen, and it'll remove the other errors from the screen and open up a window which contains, for that particular error that you've selected, the name of the error, what kind of an error it is, and a possible way of fixing the error. It is spelled as it''s, whereas it should have been ITS. You can select that with the light pen, and that replaces the incorrectly spelled one in the text. We see it being used as a general sort of proofreading capability which can be used for, well, say in a publications environment. You can have it do the sort of tedious job of proofreading the entire text, looking not only for spelling errors, but for simple or even complex grammatical and style errors, too.
Computers also like things that are strictly right or wrong. You know, they like yes-no answers, they like numbers, they like to be able to add things up and put them together and get a result. Language is much less that kind of a symbol system. It has a different life, it has a different purpose. Its purpose is communication. And communication is not something that is either yes or no, right or wrong, but is various shades of success or failure. And to understand and grasp that kind of a complex, multifaceted system is something that no computer program has ever been asked to do before.
There are two aspects to expert systems. There is the understanding, the intelligence part of artificial intelligence, and there's the technology itself. And in many cases, what are termed expert systems are really slightly dumb systems that exploit the speed and cheapness of computer chips. The chess programs available do not really understand how to play chess. They don't look ahead infinitely, but they can look ahead and calculate faster than most human beings, than all human beings, and play reasonable chess. But they can't understand issues like gambits and sacrifices. There are many expert systems in the literature which are nothing more than a series of fast if-then-else rules. If it's this, try this. If it isn't this, try this. Isn't this, try this. And you do that a couple 100,000 times. It can look remarkably intelligent. The real issue is understanding our own understanding. Let me give you two sentences which seem very similar, but are very different. Time flies like an arrow. Fruit flies like a banana. Now, how do we ourselves tell the difference between those two sentences? The major contributor to artificial intelligence has historically been philosophy, cognitive psychology, and linguistics, theoretical linguistics. It still should be. Chips are not going to solve the problem of understanding.
So the system is quite capable of correcting this to read, the yolk of the egg is white. But it's a long way from knowing that the yolk of an egg is yellow. It's easy to see this as a database. They're numbers and letters that computers familiarly handle. But this is also a database. It's a map, and it could soon be possible from my computer terminal to find out how to get, for example, to Zermatt in Switzerland, or even to find out the best way from my office to a good restaurant. This is where the transistor was invented 30 years ago. One of their latest developments is a database of a quite novel kind. Instead of just text, it holds images.
It's a conventional street map. It has all of the streets, the rivers, the railroads, lakes, and municipal boundaries.
I'm in the Mayflower Hotel, which is on Central Park West and 61st Street. Can we find a restaurant, a good restaurant within walking distance of the hotel?
Right. This is the overall map of the New York City area. And what we can do now is to say, well, we'd like to look in particular at this area in Midtown. So I'll say that I want the map centered in Midtown and just cover Midtown Manhattan. I've just picked the edge of the map. And now I choose from this set of options and say that I want to zoom in. So I'll now get a map with center there and edge there so that it should cover roughly that area. And indeed, the map goes from just about the Hudson River on the left side. You just barely go to the East River. So we say to the program, where is there a good restaurant within 10 blocks of your hotel at 61st Street and Central Park West? You want some restaurant that some restaurant reviewer gave 2 stars to. And we have a file of 300 or so restaurants. And so here's the list. And this one is Continental Restaurant, another steak restaurant, Turkish restaurant.
Gallagher sounds a good one.
Okay. So now we'd say we'd want directions to 228 West 52nd Street.
The route it produces, in this case for a car, can take note of one-way streets, the number of left turns, and even the average traffic speed.
There are many possibilities, because you can imagine it being used, for example, in a car, in connection with some kind of advanced mobile phone service, in which you would actually call in from your car terminal and get directions, and in which you can even imagine that the computer was tracking the car in some way, so that it could tell you when you had to make your turns by knowing the position of the car, which might be done either by tracking it through the radio signals or by connecting the device to the odometer in the car so that it knew how many miles you had gone. You can also imagine a service like this being available in places like hotel lobbies or gas stations or airports, so that people needing to ask questions could get personally drawn maps with sets of directions.
The technologies which find a market, the ones which quickly get assimilated, are ones where they're fun, they're challenging, and they're what I would call mundane. You can take them for granted. And the telephone, again, is a good example. One uses a telephone with no real idea of what's behind it. One shouldn't have to. I think also people should use the tools they enjoy. I don't think there's anything special about using a computer. For example, this is one of my favorite possessions. It's a very old-fashioned instrument which hasn't changed since probably the 19th century, and I use it to write articles about the wonders of the electronic office. The notion that I should use a word processor for that is one I simply won't accept. I just like using that. It's something which is part of me. And I think when we look across to technologies we use every day, cars, watches, TVs, we're very fussy. We want a certain number of functions, things they do well. One doesn't buy a calculator which can't add. On the other hand, we're very concerned about, is it comfortable to hold? Does it look nice? Does one just like it? And the challenge in the electronic office is increasingly not around functionality, but ease of use.
Ease of use is a phrase we often hear, particularly when referring to microcomputers. Well, what does it really mean? Well, it means they're hard to use. To me, ease of use means having a microchip on your thumbnail, and you can say results, and you can hear your results. More detail, and you listen to more detail. Projection, and you can project your graphics on the wall. That's real ease of use. Apart from the keyboard, which is intimidating enough, you've got floppy disks, you've got file names, and so on. And you've got an enormous amount of documentation from spreadsheets, data management, different operating systems, different languages, and every one of them fails the drop test. There's a real need to reduce the number of commands needed to drive a computer to an absolute minimum. An interesting development is business software which aims to be quick to learn, easy to use, and versatile. Called Office by Example, OBE for short, it's able to deal with spreadsheets, data management, word processing, graphics, and electronic mail, all totally integrated and using very few commands. It's the brainchild of Moshe Zloof.
The main thing here is its ease of use, because people who are non-professionals, like executives, secretaries, clerks, are people who are going to use OBE. So what we started from really is was to ask ourselves, is there any fundamental set of operators by which if you master them, then you are mastering a big domain, a large domain of facilities. Now, if I want to find out what menus do I have, I write a P dot. And then I get the list of all the menus. Now, one of them is called Zloof, which I set up. Then if I want to see that one, I just write P dot in front or beside it. So while in other systems you have to remember maybe 15 different things for storing, like insert, store, define, create, and so on, here you have only a single operator called IDOT. Okay, so what happens is that when people develop these things, and they are kind of separate, develop a spreadsheet separate from a database, separate from a graphics, you have to almost repeat all these in different semantics, different operators. Okay, so you might have in one system D stands for down and U stands for up. In another system, U stands for update and D stands for delete. Okay, and the point is that that although the people who developed those systems were very consistent within the system itself, but when you try to have them talk to each other, the user is going to be very confused because you have to move from U update to U up, or D delete to D down. Okay. And so we try to look at it from a much more general point of view to say, let's kind of address all these problems and see, can we come up with a unified interface with very simple commands.
What I think the better software designers like Moshe are trying to do is just open up the range of possibilities. Very different from the concept of automating. When we automated work through technology, we were almost force-fitting people into a mode of operation. If you work in a data processing environment, you do what the computer tells you. Moshe's idea, obviously, is to make it possible for the computer to do what you tell it. And there are many possibilities, is a good phrase. We don't know what many of them are. The tools shape the uses, and the uses shape the tools. Once again, modern technology will stand or fall by flexibility and naturalness of mode. And that's very difficult to build.
Moshe Zloof gave us a flavor of how OBE works.
Now, see, this menu has many options. For example, if I want to send mail, I set up my own template, so I can just place the cursor under send mail and hit enter, and the system will give me another window on top of everything that is already set up for me, and I can just type whatever, hello, as an example, and so on. And then I can send it. And already the command box is set up, so I don't have to remember S dot, which stands for send. I don't have to remember that. And I can send it to other people. By the way, I can send it also to myself. For example, if I write here ZLOOF and I hit enter, you will see the system will say from the desk of Zloof, send to Zloof. But since I am Zloof, I get you have a new mail from Zloof. If I want to actually see my mail, I go and hit PF12. Now the system displays another window on top of everything. Now we have three windows. One is the mail, and you can see the last one says hello, okay, the one that I just sent. And all the mails that I got today or before, it's stacked. Now I go up and erase that window. I'm back into the window called send mail that I just created. Then I can erase that, and then erase the window, and then I'm back into my menu.
What Zloof would like to do is to get all the instructions on one sheet of paper, and if he could, it would certainly pass the drop test. But still today, we're faced with a keyboard, with a large video display unit, incomprehensible operating systems, and a bewildering array of application packages. And I think it'll be a long time before I'll be able to say results and get any sort of sensible reply.
That was the last programme of this series, but Ian McNaught-Davis will be back in 3 weeks when he presents the follow-up to last autumn's MicroLive programme and announces the winners of the BBC National School Software Competition. That's MicroLive on Sunday, 24th of June at 12 midday here on